Hey everybody, this is Larry. This is day 29 of the LeetCode Daily Challenge. Almost to the end of the year. Congratulate yourself if you're watching this or just solving problems, I guess. Hit the like button, hit the subscribe button, join me on Discord, ask me questions there, here, wherever you like. And usually I solve these live, so if you want to skip to the solution, I guess fast forward or something like that, because I usually go over my thought process instead in the beginning. Okay, so today's problem is pseudo palindromic paths in a binary tree. I feel like they could have maybe tried a little harder to make it an alliteration, but that's okay. Pseudo palindromic paths. Okay. So given a binary tree where nodes are 1 for the 9. Okay. If at least one permutation of the nodes of the path is a palindrome. Okay. So this is a little bit. I think I solved this problem either on a LeetCode contest or something similar. So I think I have an idea about this. The key thing to note immediately is the 1 to 9 part. So 1 to 9, what does that mean, right? That means that, well, there are two things, I guess. 1 to 9 is a critical part as well, but there are only 9 objects or 10 objects. 9 objects? Yeah, 9 objects inclusive. So keep in mind in that as we go for it. The n in this case doesn't matter because we have a linear time solution in my head, and that is depth first search, or just recursion, I guess. Actually, I actually have gotten a little bit a bad habit of calling everything depth first search because everyone, for some reason, keeps on calling normal recursion depth first search. But yeah, you could kind of think about it as an implicit tree, but this is an actual explicit tree, so I don't know. Anyway, linguistic and languaging aside, so this is going to be recursion, and the thing that, or even backtracking, I think maybe a better way to put it. And what is the backtracking? Like, how do you backtrack, right? Well, the key thing to note is kind of defining pseudo palindromic another way. So a binary tree is said to be with at least one permutation of the node values in the path as a palindrome, right? And some of this will require you to have played around with palindrome problems before, and these properties that I have done, I guess, enough times to be able to solve this or able to kind of figure this property out immediately. But if you haven't, then you may have to play around with what it means to be pseudo palindromic, and if you don't remember it, or if you don't remember from previous time that you solved it, I'm going to go over the property for sure, but I think the best way to remember it, or not remember it, but just like understand and learning stuff like this, is just by actually discovering yourself. Because if I'm going to tell you now, and that's fine, and but the problem with that is that instead of actually like thinking about how to or why things are, you're just going to memorize a fact, and it becomes trivia, and it becomes harder to remember next time, right? So definitely play around with it if you haven't. But the thing about pseudo palindromic is that, okay, so what's a palindrome, right? Palindrome is a word that goes that is the same backwards and forward. So there are two classes of palindromes, I want to say. Maybe, I don't know if that's the right name, but basically they're palindromes of even length or odd length. But if it's even length, let's say you have 1, 2, 3, 4, 4, 3, 2, 1, then the first characters you go to the last character, second characters you go to the second last character, and so forth, right? And there could be repeats, so you could insert a 4 here in the second place and the second last place, right? And the key thing to note here is that for a even length number, or even length string in general, notice that whenever there's a character in the beginning, that means that there will be a character at the end, right? I mean, that's an obvious statement. That is the definition of palindrome. But what does that mean, right? That means that if you want to count the number of ones, in this case, there's always going to be an odd number, right? Oh, sorry. There's always going to be an even number of ones. I said it wrong. My bad. And what I mean by that is that you can think about it as, okay, this 1 cancels out with the 1 in the back, right? So it is still even. The 4 cancels out the 4 in the back. The 2 cancels out the 2 in the back, and so forth, right? So for even length palindromes, so you can construct a palindrome if for any string, it could be any string now, right? Something like this. If there's even number to cancel out, right? So like we put this in the front, we put one in the back, we put two in the front, we put two in the back, and so forth. So all we need is, here in this case, right, is every character appears even number of times, right? And then odd length palindromes is similar but a little bit different, and maybe you know where I'm going with this already, which is, you know, there's just one character in the middle that is the same with itself, so therefore it is the odd one out, so to speak. No pun intended, but maybe a little bit intended now that I think about it. So here, then the condition is similar to the other one. Every character appears an even number of times, except one character, right? So those are your two conditions for having a pseudo palindrome, because if that's the case, then you could rearrange it to be a palindrome by very trivially, and by trivially I mean like, okay, given a string, can this and we know that this is a palindromic string, can you construct a palindrome, right? And the answer is just yes. You sort it, it's greedy, so you sort it to something like 1 2 3 4 2 2 3 3 5, something like that. And then, you know, and then for every other character, you just wrap it around like on the outside or inside, doesn't matter, right? And then the odd character, the one character that you're allowed to have, you put in the middle. So basically, those are the so that's the observation about pseudo palindromes that you would have to know, right? Okay, so those are the PPP. So then now, and I obviously recommend that you get familiar with recursion, tree problems, and so forth, because this is probably not the or shouldn't be your, you know, earlier. Like if you struggle with tree problems, definitely there are easier problems to work through first. But now, you know, all we have to do then is just track whether every character appears even the odd number of times or even number of times, and that's pretty much it. So now we go back to the first thing that we noticed, which is that the digits can go from 1 to 9, and because of that, we're able to just, and in a very naive way, for example, pass in an array of length 9, right, or something like that, and or you could pass in a set. There are different ways you can do it, and we're gonna implement it afterwards. And also, if you're very slick, you can upsolve it with bit masks. If you're unfamiliar with bit masks and you want to get better at bit masks, this may be a good problem to practice that. And I'm not going to go that way, though. To be honest, if I'm doing it in competition, that's what I would do, and I think that's what I did during a competition. I could be wrong, but yeah. So yeah, so now I'm going to just implement this with set. So let's go. Okay. So then there are two ways to do it with these with recursion problems. I'm gonna do so there is like a way where, and I see this a lot, and I do it a lot too, to be honest, because it's easier to write. Where you have a global variable, and then you do total. You have a recursion. Let's just call it PPP because pseudo palindromic paths. Node, and then some conditions happen. Total right? Like if something is true, something like that, right? So that's definitely it works, and you can definitely do it that way. But I'm going to try to if you're struggling with recursion, this is kind of a little bit of a hack that I wouldn't recommend to beginners. What I would recommend is try to express the answer in terms of the function itself. And what I mean by that is that, okay, now we can do something like, okay, total is equal to 0. If something is true, total plus equal to 1. And then total, maybe, plus is equal to PPP of no dot left, total PPP of no dot right, and then return no total. And then now you could do, or well, actually, you should have done it the other way in reverse, to be clear, which is that you define this problem as the total. So this function returns the total number of pseudo palindromic paths at this point, or something like that. Something like that, right? So you have to define that, given that we have seen these digits. I forgot a parameter for this particular specific problem, but again, this is just an outline of what I want our code to look like, because then now we can just say, okay, well, that matches up with what we want, which is just return PPP of the root, right? Okay, so that's basically how I would think about it. Definitely try to have this, I wouldn't call it template, but just this idea of, for a lot of problems, it is able to kind of contain the problem within the function itself. So then, there's no interaction explicitly, and then you don't have to, it forces you to think about recursion problems in a recursive way that isn't abusing some global state. Okay, so now let's actually write this. What do we want? Okay, so we have to, let's say we have a set of the characters that we have seen. So now we start with a set, right? So again, we said total is equal to 0. If something is true, well, what is true, right? Is this the true is if this is a leaf. So if node.left is equal to none and node.right is none. So if this is a leaf, what happens, right? Okay, if this is a leaf, and this maybe I'm skipping a step a little bit here. So let me go back for a second. If if every character appears even number of times, and the thing that I want to point out here is that now we're like, okay, we actually need to categorize this. We have this scene thing. So the way that I would implement this is because we only care about the even number of times, so we can actually just keep track of so scene instead of a set that represents, because you can also use a or use a dictionary and just keep track of the number of times you've seen something, and then backtrack that way. But because we only care about the parity, which means whether it is odd or even, we can say we can actually just change this to even. And what this means is that the characters that are in even, actually I guess this is odd. Whoops, my fault. Because the characters that appear in odd appears odd number of times, and then when because then now in the beginning all the characters are even because there's 0. Then it goes into odd as they get added, and then the second time you do it, you remove it from odd. So that's kind of my strategy and how I want to do this. So yeah. So then now we can do something like yeah, and this is way I wanted to write it like a regular backtracking. So that means that, okay, so the current character, I guess technically we're doing camel case. Current character is equal to node.ryu, I think, right? And we know that this could be only 1 to 9, but so if current character is if it's in odd, then we remove it, right? Because now it's even. Is it remove? I think that's the current. I don't remember the library that much. Otherwise, we add it to current character, right? Okay, and then now we do the recursion for the left and the right, and then and technically for backtracking, you actually want to clear up the state before every recursion, but it depends on what changes, right? In this case, we actually have the same state that we want to pass through, so we're going to save the fix up for in the back at the end, and basically we just kind of do the opposite of this thing, which is actually the same code because it is invertible. Because again, if this is an odd, we have to remove it. If it is not an odd, then we take it back out, right? So this is the opposite of that, even though it is exactly the same code. Okay, so then now we can check whether the character appears in if every character appears in a even number of time, and that is if the length of odd is equal to 0, meaning every character is even, or length of odd is equal to 1, right? And I know that you could write this actually as but I just want to be explicit for a little bit. Yeah, and that's mostly how I would do it. Let's kind of give it a quick run. Probably have some typo somewhere. Ooh, no left. Oh yeah, in this case we can actually return total right afterwards, because, huh? Yeah, I usually write something like if no is none in the beginning, but I guess I just forgot about that one because I was talking about the other cases. But yeah, and we can return this immediately because all this stuff just goes to the left and right, which we know is none, right? So let's run it again. Okay, so that's not great, but oh, the reason why this is the case is, well, I don't know if this is the only reason why, is because we didn't add this to the, we didn't add the current node to the thing before checking. So let's actually do that. So we should put it in the front. Huh. Dun dun dun. That's interesting. What am I doing wrong on? Usually I would say it's something silly, like I forget to process root or something like that, because you have to make sure about your conditions, or your precondition, that is. Well, nothing like someone told me this notation, so I'm gonna try it, even though I don't think this makes sense for the node. But let's take a look at my recursion. I actually expect this to be right, to be honest. So let's see. So at the beginning, we go from the root node, and the set is none. Then we recurse on the 2 on the 3 side. What does this graph look like again? 2, 3, 3. Let's put this after we take a current process. So this should be good. What is the 2, 3, 1 maybe? How did this happen? And I think I'm sharing state by accident somewhere. Let's see. Or I'm not reverting correctly. If odd isn't, yeah, this should be okay. Why? I'm doing something sloppy, clearly. And to be honest, the way that I usually do this is by creating an other example of odd, and that way you don't get tangled, but it creates an additional cost. So let's try next, or this odd maybe is you go to set up odd. So yeah, also got giving camel case, because then here, just want to see if this was the reason. There is a little bit. Oh, it should be okay with backtracking. So there are 2 ways to do backtracking. Is either, I mean, there are multiple ways to do backtracking, but so this is right. So maybe I did the references in a wrong order. Because for this one, the thing that I would worry about is that there are interactions that are a little bit weird with respect to the. Oh, I know why. Actually, so I think this is, I mean, if I did it this way, this would be right. And this is one of the 2 ways to do it with backtracking, because basically what I did is that I create another copy of the input, so then there's no references to the same thing. But the problem was that I moved this to up here, but then, and that means that here I returned without removing it. So that's a little bit messy. That's a little bit sloppy, rather. Well, both maybe. So if we had done this, it would have been okay, but that's obviously really yucky code. Yeah, so that would be okay. So what I would also sometimes write is just a helper function. Toggle char if char in odd that remove char. So something like that. And then now we can just toggle current char. And I think, to be honest, if I didn't add this return total early, even though that would still be okay. I think when I added it, it confused me a little bit because it has early termination, but because of backtracking, you know, it becomes not right. Yeah. Okay. So, and I would also say that, well, I'll talk about how I would code this during competition later. Okay, looks good. So some of my little bit sloppiness is because I don't usually do it this way. To be honest, I code it this way, hopefully in what I think is better for learning, and it, descriptive as to backtracking and how to kind of go through it. But if I were to do this on a contest, and I might have already done it, I would do it another way. Let me see if I could find this on the on my previous code. But while I do that, so what is the complexity of this, right? Well, because we look at each node once, because this is essentially a pre-order traversal or depending on how you define it, but it is a backtracking, and we look at each node constant amount of times, just once. This is going to be linear time. Yeah, that's all I have for this problem, really. Yeah, and in terms of space, well, set, where's the set? Well, this set is going to be adverse over 1 because there are at most 9 items from 1 to 9. However, the recursion tree depends on the height of the tree. So your recursion core stack is going to be O of h, where h is the height of the tree, which could be adverse O of n for like a linked list like node. Let me take a quick second to see. I think I did this problem during a contest, so I could just show you what I did during a contest, just to kind of give you a little bit sense of what's going on. I guess this is my contest code. So yeah, so when I do this during the contest, I definitely try to go for speed during the contest, and as a result, this is just my thing where, again, current is just a set, and I use a bit mask to kind of go through that as well. And there's a way to check this easier, but nonetheless, yeah. Let me know what you think. Again, this has the same complexity, but it has some properties that are nice to it, so that you don't. For me, I don't make as many silly mistakes. Debatable, but but that's what I think about it. Cool. Let me know what you think. That's all I have. Have a great holiday week. Happy New Year and all that stuff if you don't come back or whatever. I will see you later. Take care. Bye-bye.